At the end of the last lecture, I began discussing Bonferroni intervals. I'd like to finish that discussion and then move on to the time series applications of model selection procedures. And the essential idea behind Bonferroni intervals is that if we consider the probability of the union of two event sets A and B, then we know from probability theory that that is equal to the probability of A, the marginal probability of the event A, plus the marginal probability of the event B, minus the probability of the joint event A and B. Which should be written as the intersection of A and B. And because the probability of the joint event A and B is non-negative, we can have the inequality that the probability of A union B must be let's get my notes to make sure I get it the right way. Less than or equal to the probability of A plus the probability of B. This we can call the probability of the disjunction of the two events. And this joint probability, the probability of the conjunction of the events. We can also extend this result to any number of event sets A and B. And the particular application for the Bonferroni intervals arises from the calculation of the probability of type 1 error as denoted by alpha, which we have as the absolute value of the test statistic for the first restriction being greater than the critical value from the t distribution with epsilon 1 as the significance level, and the absolute value of the test statistic for the second restriction being greater than the critical value for the t distribution with epsilon 2 as the significance level for that test, on to the absolute value of the test statistic for the rth restriction also being greater than the critical value for the t distribution at significance level epsilon r, when in fact the null hypothesis, which is the joint event of all those restrictions being true, is true. That is the probability of type 1 error. So that we're rejecting H0 when in fact H0 is true. And using this relationship, the probability of the disjunction, we can say that that will be less than or equal to the sum, I is 1 to r, of the epsilon i's, where these epsilon i's are in fact the probabilities of type 1 error on each of the separate tests. And so we can now use this result, which is ignoring the probabilities of type 1 error arising because these test statistics are not independent. We're ignoring that and just taking the disjunction. We can use that result now to put a bound on the probability of type 1 error for the test as a whole. In other words, we can put a bound on alpha. For example, if we now test our hypotheses in this way, in other words, using Bonferroni intervals, that's testing each restriction separately, using Bonferroni intervals, we can ensure that the probability of not rejecting H naught which is the composite hypothesis embodying all R restrictions. So we can ensure that the probability of not rejecting H naught when in fact, when H naught is true, in other words, that's 1 minus alpha, is at least a given or chosen probability, which I'll denote by P. And that P is 1 minus the sum of the epsilon i's. And we can do that by an appropriate choice of the epsilon i's. So we're saying if we do test each restriction individually, and we're careful in the choice of the significance levels for each of those tests, we can ensure that the probability of us accepting H naught when in fact it's true is at least some pre-assigned value, which I call P. And we do that using this inequality on alpha and the sum of the epsilon i's. If we now consider a particular example, and let's choose P to be 95%. In other words, we're saying alpha, we want to be a conventional 5%. And also, to simplify the calculations, we'll assume that all the epsilon i's are equal to a common epsilon. So we're going to use the same significance level for each test. Then we know that 0.95 has got to be equal to 1 minus R times that common epsilon. So that epsilon will now depend on R. To make it a more concrete example, if we're going to test 4 restrictions, then epsilon would be 0.0125. And the implication of that is that 1 minus alpha, which is the probability of not rejecting H naught when H naught is true, will be greater than or equal to P, which is equal to 1 minus the sum of the epsilons, which here is R times the common epsilon, which will be 0.05. In other words, it is 95%. Well, that's the theory of the Bonferroni intervals. What are the implications of it? Well, the implications are that for each of the individual tests, we're going to be using small sizes or small significance levels to ensure an overall 1 minus alpha, for example, equals 95%. That therefore means that the critical values from the t distribution are going to be larger than they would if we use conventional significance levels. And so the Bonferroni confidence intervals are in general larger than we would get if we were able to evaluate this probability alpha directly. And the reason for doing the Bonferroni intervals is that in general, when these test statistics are not independent, the calculation of this probability can be quite complicated. So rather than evaluate that probability so that we can control the type 1 error probability, alpha, we control a bound on that probability rather than the probability itself. And the cost of doing that is that the confidence intervals are larger than they would otherwise be. And that's exactly the same situation as the simultaneous confidence intervals, because the simultaneous confidence intervals are also larger than conventional confidence intervals. But you are able to show that in general, the Bonferroni intervals are smaller than the simultaneous confidence intervals. And that's not a surprising result when you remember that in the simultaneous confidence intervals, we're testing whether any linear combination of the restrictions is significant or not. Whereas in the Bonferroni approach, we're specifying a particular set of restrictions, which needn't be all the restrictions which are generated by the composite hypothesis H0. To make that a little more concrete, if H0 is R beta is equal to B, then with the Bonferroni approach, we may well take each of the restrictions in R beta equals B separately, and only those restrictions, and perform tests on those. Whereas with the simultaneous confidence intervals approach, we take all possible linear combinations of the restrictions. So that there are many more restrictions to be tested in the simultaneous approach than there are in the Bonferroni, and so it's not surprising that the Bonferroni intervals are in fact smaller in general than the simultaneous intervals. And as soon as we move to time series problems, we often come to hypotheses and test statistics which have this structure, that the test statistics really are not independent, and if we want to control probabilities of type 1 errors, it is difficult to calculate the type 1 error. Therefore, to use Bonferroni intervals is quite a convenient approach, and usually more applicable and more relevant than simultaneous confidence intervals. So I now move on to time series applications of model selection. And the models that I want to consider have the following form. Where yt is a dependent variable. And I'm using econometric notation here so that the yt is an endogenous variable. The vector zt is a vector of predetermined variables. So that can be strictly exogenous variables determined outside of this system, and in particular distributed independently of the error term ut, or lag values of endogenous variables, and in particular lag values of yt. That's in general. But for this specification, I've introduced a polynomial, a scalar polynomial in the lag operator L, so that in fact the lags of yt I've removed from the explanatory variables on the right-hand side and brought to the left by using this polynomial, beta p of L. The p there, subscript, denotes that this polynomial in L is of order p. So that beta p of L will be beta naught plus beta 1 L plus beta 2 L squared through to beta p L to the power p. And L is the lag operator such that LP times the variable xt is in fact xt minus p. The Q subscript on the vector polynomial gamma of L denotes that the maximal order of the polynomials in that vector is Q. For any individual variable I within the vector zt, the corresponding polynomial will be of order Qi, so that it's not necessary that all the polynomials in that vector of polynomials are of the same order. They could have different orders. But Q denotes the maximal order. So that's the structure of the systematic part of the model. I now want to introduce the structure on the error terms. And the errors are assumed to be generated by an autoregressive moving average process. The autoregressive part is rho of L, which is a scalar polynomial in the lag operator L of order R, and that is equal to mu of L into epsilon t, where this represents the moving average component, and mu of L is again a scalar polynomial now of order nu. So the class of models that I want to consider the model selection problems for are models made up of 1 and 2. Usually, I'll assume that the errors epsilon t are white noise, normally distributed, constant variance sigma squared, and serially independent. In fact, this assumption is a convenient one to make. It's not always necessary to get the results. Well, first of all, why should we be interested in models of that type? Because they may look particularly restrictive. Well, a model of that type could be a single equation out of a dynamic simultaneous equations model. So we could have a model, again, in usual econometric notation, where we have, say, a system of n endogenous variables, and the n endogenous variables at time period t are in the vector y with the tilde underneath. And then the coefficient matrices are the coefficient matrices in a matrix polynomial in the lag operator L, so that beta p of L is B0, which is the usual coefficient matrix of the current endogenous variables, plus B1L plus B2L squared, and so on up to P. A similar definition of CQL, that's a matrix polynomial in L of order Q. And we have the error terms. Well, the error terms can now be generated by a vector autoregressive moving average process, so that we have R of L ut is equal to M of L epsilon t. And that's a structure for dynamic econometric models or dynamic structural time series models, which has been discussed in the literature and which has been applied in the literature. Equations of the type 1 and 2 could be a single equation out of that simultaneous structure. So that's one reason for being interested in this structure. The second reason why we might be interested in this structure is that there has, in recent years, been an increasing interest in univariate armor models. And if we consider an armor PQ model, then we have phi of L of order P, yt is equal to theta q of L eta t. And this would be a univariate armor PQ model. And these are now very familiar following the work of Box and Jenkins and other people. But certainly it's Box and Jenkins who've made it as popular as it is at the moment. And this would be a model contained within this general set where we're setting the vector polynomial gamma of L equal to 0. And we can also say that we're in fact setting R equal to 0, so we're removing this autoregressive component. In fact, in that univariate model, we couldn't separately distinguish rho of L and beta of L. So it's arbitrary whether we restrict R to be 0 or P to be 0. All we're saying is that we can't separately identify P and R. So I opt to say that this model is this general one with R set equal to 0. So again, if we analyse the problems for this model, they will help in the analysis of univariate armor models. And the third reason why we might be interested, common to econometricians, and that is because of distributed lag models. So that we might have a variable of interest yt expressed as an infinite weighted function of the lags of some variable xt plus an error term ut. So that again, w of L is a polynomial in the lag operator which might be an infinite order polynomial. And a great deal of the literature on distributed lags has been concerned with how can we get a finite parameterization for models of this type when perhaps we are assuming initially that this lag distribution is of infinite order. If it is of infinite order, we know we can't estimate it in that form. Therefore, what finite parameterizations are available and how good an approximation will they give? Well, perhaps the most famous approximation is the Coic distributed lag. But more generally, we might use the rational distributed lag as an approximation. Which would mean we're saying that the W of L polynomial can be approximated by the ratio of two finite order polynomials, A, which is of order P, and B, which is of order Q. If we do that, then the model becomes BQ of L yt is equal to AP of L xt plus BP of L ut. So this model, again, has a form which is contained within the general model I want to consider. But one of the major problems in distributed lags of this form is the determination of Q and P, the length of the lags. If we go back to the univariate armor processes, one of the major problems here is the determination of P and Q, the orders of the autoregressive and the moving average components. And in the more general context, the major problem in the simultaneous dynamic model is again the determination of the orders of lags within the model. And so if we're able to say something constructive about the determination of the orders of lags in this model consisting of 1 and 2, that should at least be helpful in pointing directions where we can solve the problems for these other cases. Before going on to consider those problems in detail, that is the determination of parameters like P and Q, let's first of all look at some of the reasons for dynamic models. By dynamic model, all I mean is that there are lag values of the variables involved in it, so that we do get polynomials in lag operators. Well, the main reason, I believe, for dynamic models is that we want to capture the distinction between long-run and short-run behavior. So we've got the long-run and short-run behavior. And it's commonly believed in economics, for example, that behavior in the short run will differ in many circumstances from long-run equilibrium behavior. Well, why does that come about? Well, one of the primary reasons for a distinction between the long run and the short run is the presence of uncertainty. If we knew what the value of all variables for all time periods, including time periods in the future, are going to take, then we really have very few problems in taking decisions at any one point in time. However, if we do want to know for some reason the value of a particular variable at some point in the future, then we have to estimate that particular variable in the future, and we have uncertainty introduced at that stage. When we're doing that, how could we introduce expectations? So we're now saying because of uncertainty, we will form expectations as to the values that particular variables are going to take. We don't know with certainty what the values will be. We'll form expectations. Well, how could we do that? Well, one of the most popular ways of modeling expectations in econometrics has been to use, for example, univariate armor models, so that it's a purely extrapolative expectation. If you need to know the expectation of the variable y at some time period t, then via the extrapolative method, you'll be forming that expectation simply using information on the past values of yt. So you'll get your expectation of that as a function of yt minus 1, t minus 2, and so on. And a univariate armor model would be an example of an extrapolative generation of an expectation. But that doesn't use any structural information you might have about the behavior of the variable yt. and economists believe that they do have structural information about the relationships between variables. This leads us to another method of generating expectations. And this is known as rational expectations. And by rational expectations, what is meant in loose terms is that when you form the expectation, you use all the relevant information you have about that particular variable. And in particular, if the variable that you're wanting the expectation for occurs in a simultaneous equations model, then all the structural information that you've built into that simultaneous equations model ought to be used in forming the expectation of it. If in fact you didn't use that structural information and simply use an extrapolative method for generating the expectation, you're ignoring some of your supposedly valid information. And therefore, in rational expectations, you do have to use that structural information. And so we can see that if we do use that information properly, even if our original simultaneous equations model is a static model, via rational expectations, we will generate dynamics into the model. So that if we now assume that we have a static simultaneous equations model, so there are no lags at all in that model. Yt is the vector of endogenous variables. Y1t star, the 1 is introduced to denote that that is a sub-vector of the vector yt. The star denotes that these are expectations of those endogenous variables. Zt are just exogenous variables, and ut are error terms. So this is a completely static model, but with expectations of a subset of the endogenous variables included. Well, if we look at the reduced form for that model, we have minus b inverse c y1t star minus b inverse d zt and plus b inverse ut, which, if we now ignore the restrictions from the structural specification, we can write as a coefficient matrix pi 1 into y1 t star plus pi 2 zt plus vt. So that now is the unrestricted reduced form for this static model. Our problem in implementing estimation of this model is that the expectations are non-observable. Where if we now use the rational expectations hypothesis, we know that y1t star should now be equal to the expectation of y1t conditional on all the information available up to the time period t minus 1. And that's omega t minus 1 is just denoting all information that is available. Notice that there's no point in considering the generation of expectations simultaneously, in the sense that we will form the rational expectation of y1t using all information available up to time t, because the information up to time t would include yt or y1t. So that this is the rational expectation of the variables y1t formed at t minus 1 using all the information available at time t minus 1. So this is the important step in rational expectations. All we now have to do is to see how this can be obtained from the model. Well, the first thing we have to do is to partition the reduced form, because we're only considering a subset of the endogenous variables. So y1t will be now equal to pi 1 1 y1t star plus pi 1 2 zt plus v1t, and y2, the remaining endogenous variables, are pi 2 1 y1t star plus pi 2 2 zt plus v2t. So now, using this relationship, we can now take the expectation of this first equation, or first set of equations, and we take the expectation of y1t conditional on all the information available up to time t minus 1. And because when we take that expectation here, we get that expression. But when we come to this first term on the right-hand side, this y1t star is in fact that same expectation. So we can now have I minus pi 1 1 into that expectation is equal to everything else in this expression. So that the result of that is that expectation is I minus pi 1 1 inverse into pi 1 2 times the expectation of zt conditional on all the information up to time t minus 1 plus the expectation of v1t conditional on all the information up to t minus 1, and we should also have I minus pi 1 1 inverse there. So if we now assume that the errors v1t are serially independent, then all this information up to time t minus 1 is independent, or is going to have no impact on v1t. So that we simply have the unconditional expectation of v1t, which is as usual assumed to be 0. So that given the absence of serial correlation in the errors, this final term will disappear. And we now have that the rational expectation of y1t is in fact I minus pi 1 1 inverse pi 1 2 into the expectation of zt conditional all information up to time t minus 1. And the implication of that is that we can only generate these expectations when we say something about the stochastic process or stochastic structure of the exogenous variables. That's as far as we can go now without saying something about the process generating the exogenous variables. Given our original specification, we've chosen the ZTs to be exogenous, and so that's presumably saying that we don't really have any reliable information about structural relationships between those variables and the endogenous variables yt. We have chosen to have those as exogenous, which presumably means we've got very little structural information about them. So that what we might do for the specification of the process that generates those is to assume that they're generated by a vector autoregressive moving average process. In other words, a purely time series process which embodies no structural information. So that we might now assume that we have a vector autoregressive moving average process generating the ZTs. And notice that that's only an example. You might make other assumptions. That implies that the expectation of ZT conditional on all information up to the time t minus 1, which we'll denote by ZT hat, the expectation, will be minus phi 1 ZT minus 1 minus phi 2 ZT minus 2 and all the other terms up to whatever order this capital Phi of L matrix of polynomials is, then plus theta 1 psi t minus 1 plus capital theta 2 psi t minus 2 plus all the other terms up to the order of this matrix polynomial. And these are the optimal one step ahead forecasts from that vector autoregressive moving average process. And we've now got the result that's needed, that in this model, if we now make our substitutions for the rational expectations of y1t, we make the substitution from this equation. That doesn't directly introduce any dynamics, but we now have to make a substitution for the expectation of the exogenous variables, which from this expression does involve dynamics. Our expectations of the exogenous variables, zt, are functions of the previous values of zt. So just by using the rational expectations hypothesis, we do, from a static model, move into the realms of dynamic models, because by making the substitution for the rational expectation of y1t, we will introduce zt minus r for various values of r. Notice that the dynamics that have been introduced into that static model are purely lag values that come from the expectations hypothesis. They have nothing at all to do with adjustment costs, delivery delays, or any of the other reasons put forward for lag values in models. We come from a static model, make it dynamic, simply by having rational expectations within it. If in addition we say that there are delivery delays or adjustment costs which cause dynamics in the model, that's another set of lag values which will come into the model, separate from, but possibly difficult to distinguish from, the dynamics caused by rational expectations. Well, that shows that if we do have expectations, we can move into the realms of dynamic models. But why do we need expectations? And essentially, we need expectations because the different time periods that we're considering are connected. If in fact we're in a world where we had perfect certainty and all decisions that we take today are completely independent of decisions we're going to take in the future, then there's no reason for having expectations and there's no reason for having dynamic models. We have dynamic models because time periods are connected. And the time periods could be connected because of delivery delays, so that we know if today we want to take a decision on what size of an order to place for a particular type of equipment. If there are delivery delays, it's going to be some time before we receive those goods. Because of that, we need to know how many of those goods we will need in the future. That decision will depend, no doubt, on future values of other variables. So it's in that sense that we would need expectations of variables if there were delivery delays. Another reason why periods are connected is because many goods are durable, so that when we buy a good in a current period, that's going to survive into future periods. And so again, in that sense, our decision today affects what happens in the future. And in particular, factors of production are durable. And the usual example of that in simple models is the capital stock. If we take a decision on investment today, that will in fact affect our production decisions in the future. And similarly, there are durable consumption goods which last for many periods. And a decision today to buy a particular durable good can have a major impact on our behavior in the future. Well, those are reasons why we consider dynamic models. Let's now turn to the problems in analysing dynamic models of the class that I want to restrict attention to. And the first problem we come into is an identification problem. And here I want to use identification in the usual econometric sense, rather than the use of identification in time series analysis, which means the determination of orders of lags. And for the class of model that I want to consider, there are some results available on classical identification. In particular, there are results by Hannon in Econometrica 1971. And there are also results by Sargan in an often quoted but not yet published paper of 1972. But the common characteristic of those two sets of results is that the orders of lags in the model are assumed to be known. So that if you know the maximal orders of all lags on variables in the model, they've analysed the usual identification problem and given conditions which can be checked for identification of the model. However, since economic theory usually gives us very little information about the length of lags, the usual situation is one where we really don't know the length of the lags, and so we would like to have results for the more general case where we don't assume that we know the lags from the beginning. Well, there's only one set of results for that case, and those have been obtained by Hatanaka in the International Economic Review in 1975, when he discusses what he calls global identification. And in fact, he's able to generate conditions for identification which are a simple extension of the usual rank and order conditions for static linear simultaneous equation models, with the major difference that if any variable doesn't occur with one particular lag, then it doesn't occur with any lag at all. So that if you have any restrictions on the presence of a particular variable saying that it doesn't occur at one particular time period, then the only time period it can occur in the model is currently. So if there are some lags missing on one variable, then all the lags are missing, which does restrict the class of models for which these results are available. But at least that does generate some criteria that can be used for testing or checking identification. In the completely general situation where we're not prepared to make that assumption that once we put a restriction on the presence of a variable at particular lags, it never occurs with a lag at all, then there are no results on identification that are available. And so, in effect, the identification problem in this general context is yet to be solved, assuming that there is a solution. Because economic theory doesn't tell us the order of the lags. What we have to do is rely on the data to provide information about the maximal lags. And that is the major problem in dynamic models. And by that I mean that if we now move on to the next topic of estimation of dynamic models, then there are really no serious problems left in considering the estimation of dynamic models. In that, if you've correctly specified the model, then you can write down the likelihood function for the model, and there are available numerical methods for maximizing the likelihood. So that if you've correctly specified the likelihood, you've used a good numerical method for maximizing it so that you are obtaining a very good approximation to the global maximum of the likelihood function, then you can rely on the estimates being consistent and efficient. It is true that for the completely general dynamic simultaneous equation model with vector autoregressive moving average errors, which I wrote down as example 1 for dynamic models, there's still a need for a published version of the full likelihood function for that model. And by the full likelihood function, I mean a likelihood function which involves the initial conditions or initial values on all the variables. There is as yet no published version of that likelihood function. But as soon as that is available, then again, there's no problem in estimating the model. And in fact, if you consider the special cases of errors generated by vector autoregressive error processes without the moving average component, or errors generated by vector moving average errors, then there are many programs available for doing that. And in fact, if we think of the London School of Economics and their work in autoregressive error processes, it's often being called the London School of Autoregression. So there are many programs available from there for autoregressive error processes. And equally, ANU might be thought of as the Canberra School of Moving Average error processes. So that what I want to now concentrate on is what I believe to be the much more difficult problem of determining the length of lags in models. I want, first of all, to look at some suggestions for solving this problem in particular contexts. And the first context is that of distributed lags. So we're considering a model which has the dependent variable yt as a distributed lag function of a single explanatory variable xt. And the n denotes that that distributed lag is of order n. It's possible that n is infinity. And much of the literature in econometrics concerned with distributed lags has been concerned with finite parameterizations or finite parameter representations of this possibly infinite distributed lag. And the COIC representation is one very simple and well-known finite parameterization. So that W of L in the COIC case is said to be beta 1 minus lambda L when lambda is positive and less than 1. So that from the infinite number of parameters to be estimated in that polynomial in the lag operator, we move to simply two parameters, lambda and beta. The other example is the rational distributed lag, when we say that W of L can be approximated by a ratio of two polynomials, A of L and B of L, A of order P and B of order Q. And in fact, in practice, investigators have been deterred from using the rational distributed lag because of the implications of that particular form. If we make the substitution, then we have that BQ of L YT is equal to AP of L XT plus BQ of L UT. And so the implication of the rational distributed lag is that in this form, which is the form we might well consider for estimation, we have lagged dependent variables involved and also a serially correlated error process, in particular a moving average process generating the errors. And though there are programs available for estimating models of that form, many people in applied econometrics, applied economics, prefer not to use those complicated procedures and would often just replace that by, say, an error term eta t, which they assume is white noise. So that the rational distributed lag hasn't been widely used in its general form. But even if we were to use the general form and use a correct estimation procedure, we do still have the problem of determining P and Q, the orders of those approximating polynomials. And in the whole literature on rational distributed lags, to my knowledge, there has as yet been no convincing suggestion as to how you should determine P and Q. There have been ad hoc suggestions like choosing models or choosing P and Q such that they maximize R squared or R bar squared and other criteria that we've considered previously. But to my mind, those are not convincing criteria for determining P and Q. So that within the realm of rational distributed lags, the problem still remains. And in fact, very little work in the literature on distributed lags has been done on determining the length of the lag. And this is illustrated by the fact that Drimes, in a whole book on distributed lags, devotes 4 pages to that problem. And the book has got something of the order of 300 or 400 pages altogether. And only 4 pages are spent on considering the problem, how can we determine parameters like P and Q. There have been ad hoc suggestions like choosing models or choosing P and Q such that they maximize R squared or R bar squared and other criteria that we've considered previously. But to my mind, those are not convincing criteria for determining P and Q. So that within the realm of rational distributed lags, the problem still remains. And in fact, very little work in the literature on distributed lags has been done on determining the length of the lag. And this is illustrated by the fact that Drimes, in a whole book on distributed lags, devotes 4 pages to that problem. And the book has got something of the order of 300 or 400 pages altogether. And only 4 pages are spent on considering the problem, how can we determine parameters like P and Q. Well, another approach to the estimation of distributed lags, where there has been some work on the determination of the maximal lag, is that via the polynomial distributed lag. So that we take our general model yt equals w of L xt plus ut, and if we now introduce all capital T observations on the variables and denote the vector of all those observations by y, we then have y equals x w plus u, where this is now a vector t by 1 of the t observations on y, x is t by n plus 1, when that polynomial is still of order n. W is n plus 1 by 1, the coefficients from that polynomial, and obviously the errors are t by 1. And it is for finite values of n, and in particular values of n which are small relative to the sample size, possible to estimate the coefficients w. But there are well-known reasons why you may not want to do that in practice, such as the multicollinearity in the variables within x, and also the fact that n might well be large relative to the sample sizes available in economics. So that one approach has been now to restrict these coefficients w to lie on a polynomial. So that we might say that wj is some function of j, and that function is a polynomial. And the polynomial we'll now assume is of order q. And the most well-known example of this is the Ullmann distributed lag. And in that case, we can write the restrictions that the coefficients or the weights wj lie on polynomials of degree q in this form, where the alpha vector is a vector of q plus 1 coefficients from that polynomial. In that case, we can transform our estimation problem to one of estimating the elements of alpha when z is x beta. We have data on x. The matrix B is also a matrix which is known, so that we can generate the observations on z. So that this now is again a least squares problem of estimating alpha given the data on y and z. Well, in this context, there has been work done on determining maximal lags. The first work that I want to consider is that of Godfrey and Poskett, the Journal of the American Statistical Association, 1975. And they consider the problem, how can we optimally determine q, and that is the order of the polynomial for a given value of n. So they're assuming that you're in a situation where you do in fact know the maximal lag, n, but how in that context can you optimally determine the order of the best approximating polynomial, or the best polynomial to give you the lag up to order n. And what they noticed is that the hypotheses about the order of the polynomial q form a uniquely ordered nest. So that q, we know, must lie between 0 and n. It couldn't be greater than n. Because if q were equal to n, we have the completely unrestricted model y equals xw plus u. And if we consider the hypothesis 1, that q is equal to n minus 1, that is the first restriction. And then the hypothesis q is equal to n minus 2, n minus 3, and so on. Those hypotheses are now uniquely ordered, so that you can apply the sequential testing procedure. But in fact, the sequential testing procedure that they proposed differs from the optimal sequential testing procedure of Anderson, in that the tests that they suggest are that you test H1 against the maintained, and the maintained is that Q equals n. You then, if that isn't rejected, test the hypothesis 2 against the maintained. And in effect, you're now testing H1 and H2 jointly against HM at that stage. So at this second test, you're ignoring the fact that you've previously tested H1 and not rejected it, and in H2 jointly testing H1 and H2. And all the tests are performed relative to the maintained, whereas the optimal procedure performs the tests against HM, H1 against HM, H2 against H1, H3 against H2, and so on. So that the Godfrey and Poskett procedure does take advantage of the unique ordering, and in fact gives you a set of valid test statistics. The problem is that that procedure doesn't have the same desirable statistical properties. In particular, the probabilities of type 1 error are different for this procedure from the probability of type 1 error for the Anderson procedure, and also the probabilities of type 2 error differ. And since it's possible to show that for this situation of uniquely ordered hypotheses, the Anderson procedure is uniformly most powerful for a given fixed probability of type 1 error, it does mean that this is inferior in terms of the statistical properties of it. But with the modification of doing the Anderson testing, then that is the uniformly most powerful testing procedure for determining Q for a given N. Another point to notice about this particular problem is that though Godfrey and Poskett proposed that what you should do is use likelihood ratio tests for each of these hypotheses, that does imply that you must estimate the model corresponding to every hypothesis. And so, again, not surprisingly, if we were to use the Wold testing principle, all we would need to do is estimate the unrestricted model. The unrestricted model is y equals xw plus u. So that's a simple linear regression model. And so ordinary least squares estimation of that will give us the estimates unrestricted of w. What we can then do is form the appropriate sequence of chi-squared test statistics as functions of the unrestricted estimates of W. So this is directly a case where the Wold principle can be very much more efficient in terms of testing hypotheses. However, this problem and its solution still says nothing about how we determine n. But still remaining within the context of polynomial distributed lags, there is a paper by Trivedi and Pagan on polynomial distributed lags, which does look at the problem of determining n in addition to determining q. And since both authors are members of ANU and the paper is an ANU discussion paper, I don't propose to go into any detail on that paper. If you haven't already read it, I suggest you do, and if you have any problems, then the best people to ask about those are the authors. But very briefly, they do mention that when you simultaneously want to determine Q and N, the problem that arises is that the hypotheses concerned with both Q and N are not uniquely ordered, and also you can have problems of non-nested hypotheses. So that if you do in fact fix the value of Q, and then consider variations in N, you immediately run into a problem of wanting to discriminate between non-nested hypotheses. And so the classical statistical approach and sequential testing at that point isn't available. And in the final part of that paper, they propose a method of simultaneously determining Q and N, which explicitly states a loss function and then goes on to analyze how you would choose Q and N to minimize that particular risk. Still concerned with Allman distributed lags, there is one more paper which has considered the determination of the length of lag. And unfortunately, again, with the Sargon paper, it is as yet unpublished, but this was written in 1976, the end of 1976, and is likely to be published within the next year. So I'll give you the title. If we consider the linear model we get using the Allman distributed lag, where now the polynomial is of order Q, and the original maximal lag was n, such that t is of dimension, x is of dimension t by n plus 1. Then for the given n, we can do the optimal sequential testing to determine Q. And that's along the lines of the modified Godfrey and Poskett approach. But if we now look at the problem of determining n, the suggestion is that since in using the polynomial restrictions like the Allman distributed lag, the effect is to impose smoothness on the form of the lag distribution, then it's probably a good idea not to have n, the maximal lag, very small. If n is small, in particular if n is small relative to q, the order of the polynomial, and we are imposing smoothness on the lag distribution, then we can run into problems where we're distorting the form of the lag distribution. However, if we let n be very large, then to impose smoothness by having a q-dimensional polynomial is going to have less serious consequences or less serious distortions on the lag distribution. And in particular, we may well find that the endpoints of that distribution do have zero coefficients. So that we can consider the best values for n by looking at tests of the hypothesis that the coefficients w at n or n plus 1 are 0, when n has been chosen to be quite large. And that's the essential idea behind the approach. And so if we now have done conventional analysis along the lines of Godfrey and Poskett for a particular n, and we've now chosen an optimal value for q, the order of the polynomial, we can now consider whether in fact the maximal lag should be n plus 1. And as mentioned previously, as soon as we do that, change the value of the maximal lag for a particular or fixed value of the order of the polynomial, we run into non-nested hypotheses. But we can approach this problem by considering a model which does in fact have the two as a special case. So we're now considering a composite model, and the form of that composite model is y is equal to the z alpha q. So those are the coefficients for the polynomial when the polynomial is of order q, and we've taken the n period lags and all the variables. We now add in x at t minus n minus 1, and we have an unrestricted w coefficient, wn plus 1. So we've just added in that final lag at n plus 1 without any restriction. We can now consider the estimation of that model, and in particular the estimation of w at n plus 1, and consider two tests. Firstly, a t-test of the hypothesis that w n plus 1 is 0. In other words, that we don't need a lag at n plus 1. And the second t-test that, or of the hypothesis that w n plus 1 satisfies the polynomial restrictions when the polynomial is of order q. And both of those hypotheses are nested within this model. What decision are we to take? Well, if in fact both are rejected, then it's saying that we do need the variable with n plus 1 lags, but it doesn't satisfy the polynomial restriction, so that we ought to consider a re-specification of the model. And in particular, we ought, if both are rejected, to consider new values for q. Because the first test, by being rejected, is saying that we do need n plus 1 lags, but the polynomial that we've got isn't such that that n plus 1 lag lies on it, so that we have to consider completely new specifications. If only one is rejected, then we can take a clear decision. If we reject the first hypothesis, then we know we need that extra lag, but we've accepted that it lies on the polynomial. Therefore, it's a simple decision that a polynomial of degree q with a maximal lag n plus 1 is our decision. If we don't reject the first and we reject the second, then we know that we don't need the lag at n plus 1. So again, a simple decision. If both these hypotheses are not rejected, then it's slightly more complicated. And if we do want to choose between those two hypotheses, the Sargan suggestion is that we choose the hypothesis that corresponds to the smaller t ratio. In other words, both were accepted. We'll choose the hypothesis that corresponds to the test, which, if you like, have the higher degree of acceptance. But that is an arbitrary decision rule. So that's one area where some work, but admittedly very little, has been done on determining the orders of lags in dynamic models. Another area is that of pure time series analysis of armor models. If we consider the armor PQ model, there have been suggestions as to how to determine P and Q, in particular by Box and Jenkins and their advocates and followers. And the first stage in their procedure, and what I now intend to give, is a very stylized and simple version of their procedure, so that if anybody's a particular devotee of their approach, it will be easy to find fault with what I say. But I think the general picture will be a correct one. The first stage would be to difference the variable yt to ensure that it's stationary. The reason being that the statistical theory for testing and for the properties of estimators is for stationary stochastic processes, so that if we have a variable which is clearly non-stationary, we would be suspicious of the test statistics that we might use. So that they would difference the variables, and secondly, inspect the correlogram for the differenced variable, and from that would hope to identify the values of P and Q. From that correlogram, they would hope to be able to spot whether it's an autoregressive process generating Y, or the difference Y, or whether it's a moving average process, or whether it's a combination of the two. And the major difficulty with this approach is that everything does hinge on very good identification at this point, because the remaining stages in their procedure go back to check whether you have identified the appropriate model at this stage. But in fact, you are able to show that those tests or diagnostic checks do have very low power against many alternatives. And that's what I want to discuss at the beginning of the next lecture, before going on to propose a different method for determining lags in dynamic models.